let's talk about something really weird. You've probably heard the old riddle about a tree falling in a forest. But what if the question was even stranger? What if the universe itself doesn't quite decide what it is until we look at it? Yeah, today we're diving headfirst into the absolutely bizarre rules that seem to govern reality at its most fundamental level. Even the great Albert Einstein was totally baffled by this stuff. He famously called quantum entanglement spooky action at a distance. And that phrase, it just perfectly captures how counterintuitive, how almost magical the quantum world really feels. And this gets us to the absolute core of the puzzle, what physicists call the measurement problem. And let's just put it simply. Why does the very act of observing something, of measuring it, seem to force it to snap into a single concrete reality from like a fog of possibilities? Now, that sounds like a complete paradox, I know. But, as the quantum pioneer Professor Carl Kocher once said, it might just be like a gyroscope. To a kid, right, a spinning top that just defies gravity, it seems like pure magic. But once you understand the framework, the physics of it all, it makes perfect sense. So could the same be true for quantum reality? Do we just need a new way of looking at things? Okay, so to really get a handle on the solutions, we first have to get comfortable with the paradox itself. So let's lay out the basic rules of this strange hidden world. So the first mind-bending rule is this idea called superposition. I want you to imagine a coin spinning in the air, right? Before it lands, is it heads or tails? No, in a way, it's kind of both. Well, a quantum particle is like that, but for everything. It exists in this probabilistic haze of all its possible states at once. It can be spinning both clockwise and counterclockwise. It can be right here and over there, all at the exact same time. And nothing shows this better than the famous double-slit experiment. So you fire particles, like electrons, one by one, at a barrier with two slits in it. If you don't watch which slit they go through, they act like waves. They seem to pass through both slits at once and create this beautiful interference pattern on the screen behind. But the moment you put a little detector there to see which slit they actually go through, poof, the wave behavior just vanishes. They start acting like tiny little particles, the pattern disappears, and reality itself just seems to snap into focus, simply because we looked. Wild. So how in the world have physicists tried to explain this? Well, for decades, the standard answer, the one you'd find in most textbooks, has revolved around the idea of the observer. This is called the Copenhagen interpretation. It was developed by the absolute giants of quantum mechanics, people like Niels Bohr and Werner Heisenberg, and their idea was just radical. They said that properties like where a particle is or how it's spinning, they just don't have a definite reality until they're measured. The universe at its core is probabilistic. So how does this happen? Well, the mechanism they proposed is called wave function collapse. So think of that particle existing in a cloud of all its potential outcomes. The act of measurement, it's like a pinprick that just pops that cloud, forcing it to collapse into one single actual outcome. And that's why the electron goes from being a wave of possibilities to a particle in a definite spot. But here's the thing. Wave function collapse is, well, it's a bit of a vague idea, right? And a lot of physicists were never really happy with it. So this has led to this fascinating battle of ideas, with at least two other major interpretations out there competing to explain reality. Okay, let's break down the three main contenders here. So we've got the Copenhagen interpretation we just talked about. Observation collapses the possibilities. Then you have the absolutely wild many worlds theory. It says the wave function never collapses. Instead, every time a quantum choice is made, the universe itself splits, and all the outcomes happen, just in their own parallel realities. So yeah, there is a universe where you wore a different shirt today. And finally, you have pilot wave theory, which argues there's no randomness at all. Particles always have a definite position, and they're just being guided by a hidden pilot wave. But as you can see, each of these has a pretty big critique, from Copenhagen's vague observer to the just sheer extravagance of many worlds' infinite universes. So what's really interesting is how modern physics has kind of added a new twist to all this. It's moving the focus away from this mysterious, conscious observer and onto something much, much more physical. Yeah, the emerging consensus is that the magic ingredient here isn't a person in a lab coat looking at an experiment. Nope, it's the simple, unavoidable fact that no quantum system is ever truly alone. It's constantly bumping into and interacting with its surroundings. Air molecules, stray photons, absolutely everything. And this process has a name. It's called decoherence. Basically, as a quantum system interacts with its environment, tiny bits of information about its state leak out and get all tangled up with trillions of other particles. And this entanglement effectively it shreds the delicate superposition, making the system decohere into a stable, classical state that we're all familiar with. And get this is not just a theory. It's a real, measurable thing. Just look at this graph. That top blue line shows a single quantum bit, a qubit, holding on to its quantum state for a relatively long time. But now, look at how steeply those lines drop as you add more and more entangled qubits. 2, 3, 4, up to 6. The coherence, that quantumness, it just vanishes exponentially faster. It's unbelievably fragile. So the crucial point here is really scale. It's all about size. A single isolated atomic qubit in a lab can stay in its quantum state for almost a minute. But a big object, a Schrödinger's cat state made of, say, 1,000,000 qubits, it would decohere in just 60 microseconds. It's just interacting with its environment too much, too fast. And that is why we don't see cats that are both alive and dead. They are simply way too big to stay quantum for any time we could possibly notice. Now, you might be thinking, okay, this is all fascinating, but it's pretty abstract, philosophical stuff, right? But here's the thing. Understanding this quantum weirdness is, and I mean this literally, the foundation of our entire modern technological world. I mean, just think about the device you're watching this on right now. The semiconductors that power it, they are a direct result of us understanding quantum mechanics. And the same goes for the flash memory in your phone, the PET scanners in hospitals that save lives, and the incredible microscopes that let us see individual atoms. All of this, not to mention the entire future of quantum computing, it's all built on our ability to control this weirdness. And the economic impact, it is just staggering. Look at this bar for semiconductors. That market, by itself, is worth over $500 billion. And when you start adding in emerging fields like quantum computing and established tech like medical imaging, you realize this isn't just some scientific paradox. It is a powerful engine of the entire global economy. So, have we solved it? Is that it? Does decoherence explain everything? Well, yes and no. The mystery isn't entirely gone. Look, decoherence gives us a fantastic physical mechanism for how a quantum system loses its superposition and starts acting normal. It explains why we don't see all these weird quantum effects in our everyday lives. But it doesn't solve that original problem. It doesn't tell us why, out of all the possibilities, we experience this one specific outcome. Why this reality and not another one? That is still a profoundly deep question. And that's exactly why this is still such an exciting and active area of research. As Adib Kabir points out in his analysis, future discoveries, maybe in quantum gravity or something we haven't even thought of, could finally tip the scales in favor of one interpretation, or maybe even lead to a completely new one. Which brings us right back to where we started, but hopefully with a much deeper appreciation for the mystery. If the act of measurement, of interaction, forces reality to choose a state, then what is the true nature of that reality when nothing, not a human, not even a single stray photon, is there to interact with it? That, right there, is the ultimate question. And the answer? Well, it's still out there, waiting to be discovered.